Hi. So as Tom just came over and told me, I should point out I'm the only driver engineer here. I'm not really a driver engineer. I sort of sit in a driver team, but don't do much coding myself. But I do have more eyes on driver development than most people here, I guess. Which is great because obviously, like Tom said at the start, this time last year, it was mostly driver type engineers, and now it's mostly games developers, which is awesome. But one of the reasons, well, one of the things that the thing I'm talking about is synchronization, because a lot of people have a lot of problems with it for a variety of reasons, and I'll hopefully try and get into a few of those. Well, I'll go through them now, actually, so let's just start. So you've got an app. You want to render some stuff, so you've got a bunch of lovely draw calls you want the GPU to start consuming. And your GPU is really, really hungry, really wants to get munching through those things and getting you some pixels out on the other end. So keep giving it stuff, it'll keep making pixels. Perfect. Why am I not in? Okay. So the difficulty is, at least with Vulkan, that it's very easy to get bitten by the way synchronization works, because it's really explicit. So it's quite hard because you've kind of got to balance things. So on one hand, you've got to keep the draw calls coming, keep the work coming so that it can keep doing stuff. You don't want to stall it, so you don't want to over-synchronize things. And in some sense, a lot of things do necessarily serialize themselves, such as texture fetches and stuff could add stall bubbles pipeline. So you want to keep it going with a lot of different things at the same time. So in the worst case, for instance, you don't want to do this sort of thing where you generate a frame, then submit it to the GPU, wait until that thing's done and start another one. I mean, I'm hoping most people here are beyond that at this point. But what you want to do is have some overlap between the CPU and GPU so that you're generating whilst the CPU's going off and doing its own thing, and you only synchronize whenever you need to reuse some resource. Similarly, on the GPU, you might have fragment and vertex work. You want to overlap all that stuff as much as possible. I mean, it's called a pipeline for a reason. GPU's pipeline stuff, you don't want to get in the way of that. The other half of it is not getting bitten. You don't, again, in Vulkan, it's very, very explicit, the synchronization you do, and you have to make sure you synchronize everything exactly as much as you need to. If you don't synchronize enough, well, bad things are going to happen. So the worst possible case, in my mind, is that nothing happens and everything just works, and you have no idea that there's a race condition in your app, which is unfortunately a very common case. But you're more likely actually to get stuff like tearing, garbage on screen, or everything just exploding and you're done. Or just black screen, which is nice, I suppose. So onto a bit of seriousness. So small caveat. Some of the bit I'm about to talk to you about is still a work in progress, but I will go through where we think we are at the moment and try to get to you. There's been a lot of work on the Synchronization chapter by myself and a bunch of other people in the Khronos group, and we're still trying to figure out the exact terminology and how things entirely work, because we're basically coming up with a memory model from scratch, but obviously taking cues from C++ and such. But there is some stuff that's still a bit TBD, but the actual fundamental technical things of what you should do shouldn't change. It just is a question of understanding. So some basic terminology first. An operation, this is just anything that might get run on your GPU. It might be a draw call, it might be a complete submit of a command buffer, it might be a single instruction in shader. Doesn't matter what, it's a generic term. If I say execution dependency, that's basically one operation waiting on another operation to finish. Fairly straightforward, I hope. Memory space, this is where the sort of memory model terminology definitions start getting a little hazy. We're still finalizing on this, where this is going. But if I talk about memory space, that's like thinking about an area of memory. It could be RAM, it could be a cache, it could be registers on your processor, or something in between. And you won't necessarily know what that is. And if I talk about something called a write propagation, this is basically something that copies writes between different memory spaces. You can think of these as cache flushes and invalidates, or physical copies between processors, for instance. And finally, a memory dependency is basically an execution dependency that includes some of those write propagations, so cache flushes and invalidates, things like that. Basically moving memory around. So this is the in progress bit, but hopefully this will aid some understanding. So Vulkan has what we're currently calling-ish memory spaces. This isn't in the spec yet, but it's part of our work. And the various ones can be accessed by different things. The key thing about memory spaces can be accessed by a different part of the GPU or CPU. So for instance, there's the CPU memory space, which is basically anything you blast at the CPU with writing to a pointer. That's CPU memory space. Don't really talk about that in the Vulkan spec, except to acknowledge it exists. There's a host transfer memory space, which is basically an area of memory, which could be a cache, it could be physical memory, it could be anything. Like on a discrete card, this might be system RAM, or it might be a cache, or some combination of the two. On a UMA system, it might just be a cache or nothing. And then there's device memory, which is when you create VK device memory objects, that's there. And then you've basically got all the different shader access in the pipeline stages. So a shader has its own memory space for each resource type, for instance. And then down at the bottom, similar to the CPU, where it's like the processor registers, you've got the shader processor registers as well. So there's a sort of vague idea of a possible memory configuration of what this might be under the hood. So that might be useful for aiding your understanding at the moment, at least. So I just want to talk about data hazards for a minute. So let's say you've got a write that you've done on the CPU to some resource. You kind of need to get that to where the GPU can read it. That's sort of what you want to do with the resource, otherwise it's basically good as useless. So you have to do a number of things to get it to be read by a shader, for instance. So I think in this case I'm moving it to the vertex shader, so let's just say it's a texture, or it doesn't really matter. But you need to manually propagate it from the processor register. You need to flush it, well, write it to the cache using, or whatever that is, using VK flush memory ranges or a coherent bit set on the memory. You then need to do a pipeline barrier and memory barrier. Oh, wait, where have I think I've lost some slides. That's helpful. And then you need to have memory barrier to get it into device memory. And you need to propagate that further to get to the vertex shader. Now, one of the things about Vulkan is because you can do memory aliasing, you can do all sorts of wacky stuff, like write to the same resource and the GPU as well at the same time via a completely different resource if you want, as long as it's aliased to the same memory. So let's say you've written out via fragment shader a color attachment, and that happens to alias the same memory as whatever you've just written to. So you've propagated that back by actually storing it, and then again another pipeline barrier has potentially pushed it over there. Now, it's worth noting that you can do this manually by guaranteeing these pipeline barriers, but all of this can happen automatically. There's nothing guaranteeing that it doesn't happen. The only thing you can do is guarantee it does happen. So if you've actually had no synchronization, this can happen if you've basically written the same memory, and you're bound to get some sort of who knows what going on. There's some undefined value in memory that might lead to undefined behavior if you access it, and all sorts of bad things can start happening. Sorry, I'm going to take a drink. So this time, let's try that same thing again, but this time we're actually going to add a memory dependency between the two. So we'll go back to here. So I've said, up to this point you can get there with a pipeline barrier. And then if we add more pipeline barriers to go back out to the GPU, and then the shader can read it, quite happy, and then only after that do we write the next one. So that can be achieved with the synchronization primitives in the Vulkan. And this is the sort of level you need to be thinking in order to be able to do safe access to your resources. It might sound a bit complicated at the moment, but hopefully it'll become clearer that it's not too bad, it just requires some thought. So synchronization primitives. There's three-ish types of explicit synchronization in Vulkan. There's stuff within a command buffer, which can synchronize between command buffers, commands in a command buffer. There's semaphores, which work between queues and a GPU only. And then there's fences, which is a whole queue operation, can be waited on by the CPU. So that's mostly useful for ring buffers of resources when you're waiting for them to see if the GPU's done with them, which I'll go into in a bit. So the first one, hopefully one of the simpler ones, but also very fine-grained, is pipeline barriers. So these are a precise set of pipeline stages to wait on. So you might say block a fragment shader waiting on a vertex stage from a previous draw, for instance. They also include memory barriers. So that's how you say, this is the data I want to move to this other memory space or whatever. And that will get you your cache flushes and correct write propagations going on. The key thing about pipeline barrier is that it is a single point in time. So it's basically, these are the commands I just recorded, then there's pipeline barrier, then there's more commands. The synchronization happens there, and then everything before, within the scope of what you've said, happens before the thing that you've specified after. Now, events are pretty similar. They give you the same information as a pipeline barrier, but they operate over a range. So you can say at the start, this thing that I've just done, I'm going to wait on. But then you actually defer waiting on that thing for the next task until you would get to recording that. So you might have a batch of work in the middle that you can do that is independent of those two things, which gives you more opportunity for overlap. Another thing events give you is actually they have a level of CPU interaction. You can actually query these things on the CPU. There's no wait, but you can get the status of them to see if they're done. And you can also set and reset events on the CPU as well, which lets you do some late latching type stuff. So say you've got some data being written by the CPU constantly, you can set an event at the point you know that it's actually ready to go, whilst already having submitted to the GPU. But you have to be careful with that because it may time out. Because there's no obvious notion of knowing when that event's going to trigger on the GPU when it's submitted, various watchdogs, kernel watchdogs, OSs might actually time you out if you don't submit the event quick enough. So it's something to watch out for. In a lot of cases, this sort of thing is unnecessary anyway. Usually it's better to defer submission unless you're doing something very specialized. You may wonder what the difference between the two, why not just always use events, for instance. Pipeline barriers are technically slightly more efficient, or maybe more efficient depending on the implementation, if you are just doing point synchronization. And they're also slightly simpler to understand, so people seem to be gravitating towards them naturally anyway. But if you do have work that you can overlap in the middle, and it's easiest to express this way, it is definitely useful to use events, but you do need to think about when you're using them a bit more. Also, the other time to use events is for CPU-GPU synchronization, for fine-grained synchronization like that. So I did say what a memory barrier, it didn't say really much more what a memory barrier was, but again, it defines write propagations. So basically between device memory and either the pipeline stage or the host transfer. And there's 3 different types. There's global memory barriers. These are the simplest. They basically, you just say, this is the type of access I did, which basically identifies whatever cache or piece of memory you're looking at. And this is where I need that memory to be visible to, which hopefully makes sense. So if, say, I've just written it from a fragment shader, I'll say my source access mask is fragment shader write, and then my my destination is I'm going to read it back on the CPU, so I'll say host access read, for instance. It does interact with the actual pipeline stages, so I think the access mask is just shader write, but then it'll take from the pipeline stage. Say you've done fragment shader, it'll go, well, that's fragment shader write, I'll flush that cache. This is mostly useful. I think someone, was it Ferrell, talked about batching of pipeline barriers. So as you'll see in a second, you can transition resources individually, but if you have a lot of resources, that might just translate into a lot of flushes of everything. So if you've got a lot of resources that are all coming from the same source to the same destination, you want to use a global memory barrier because it will flush everything all at once. And the important point here is that the user, i.e. you guys, are the ones defining the access here. The driver is not tracking any of this for you, which is where the difficulty comes in. So you do need to think about how you're going to do that, particularly if you're doing porting, where it's quite problematic because it not necessarily have that information. Buffer barriers, so this is the second type. Very similar to the global one, except you now specify a single buffer range. So if you've only got one buffer range that is relevant, you can transition that individually. That might be more efficient than doing a global one, but not necessarily. If you did 2 or more buffers, I'd suggest just using global, unless you need some of the extra functionality you get here. So the extra bit it adds is this thing called queue ownership. If you've got multiple queues on a system, which you typically see on AMD hardware at least, but you may see on other vendors as well, it's useful to say, like, any given queue can have exclusive access to a resource at any given time, and to transition it from one to the other, you have to define ownership transfer, which is what these 2 things do. Similar to the access masks, you say the source queue family and the destination queue family. Again, no tracking here. You have to specify both of them explicitly. Typically, since queues are kind of a new thing that you don't have in older APIs, this is, if you're integrating this way anyway, it's kind of slightly easy to handle that. And then the last one is image memory barriers, and these, again, very similar to buffer memory barriers, single resource, single sub-resource of an image, same queue ownership transfer semantics. The other thing, and this I know Alan is going to moan about later, I think, is the layout transitions. So again, you have an old and a new. You have to say what usage you were using before and what usage you're about to use. There is a general flag, which is any usage, but many vendors advise against that because they do get specific compression out of different layouts. The idea being that if, again, the driver's not tracking anything, so you say what the old layout is, what the new layout is, and it will do any decompression or compression it can between those usages. And it's kind of important to use these because you can, I mean, I feel bad saying it because I know our hardware doesn't care about them, but some hardware does. And it basically gives those pieces of hardware the opportunity to do extra compression and save extra bandwidth when you do it. So you do need to take care with them. I would say that if you are going to be doing a lot of very frequent layout transitions, it might be more useful to just use general rather than frequent switching because it could result in, doing the switching itself may result in a bandwidth cost. And at some point, that cost isn't necessarily cheap, particularly if you're doing it on mobile. So quick example here of texture upload. I say quick. It's a lot of text, but this is Vulkan, unfortunately. It's very, very verbose. And I've tried to pare it down to what is actually needed, but we'll see how we go. So we'll start very simply reading image from a file, and I'm pushing that straight into mapped memory. So I've already allocated a buffer here, and I've mapped it, and I'm using that pointer directly from fread. This is obviously extremely naive. You might not actually do this. I hope you don't actually do this. But then once you've pulled it into that pointer, then you can flush the map memory range. That's the first memory space transition I talked about earlier, going from host to host transfer. From there, you then need to do a memory barrier. So I've got a memory barrier for host write, because that's where I've just written it from, going to transfer read, because I'm going to do a copy from a buffer to an image. So because images have specialized layouts, they're typically twiddled and tiled, as opposed to what you might have on disk, which is a linear layout. You need to do a transfer. That's what command copy buffer to image is basically all about. So we're also going to set up an image that you're going to copy to. Assume we've already allocated and created that outside of the scope of this. But again, you need an image memory barrier or a memory barrier to say what the image access masks are. So you didn't have any access before. It's a new image, so that doesn't matter. But you are going to write to it via the transfer queue, so you need to say that, just to make sure that anything like metadata goes to the right place. And this is one place where you will need to say something about the layout. So you have to do an old layout. Doesn't actually matter. Again, you've just created it, so you've got this undefined layout, which says, I don't care about the previous contents. Just get going. But I am transitioning to transfer destination because I'm going to write to it. So I need to say that in case there is any specific compression technique that's useful there. Once all that's set up in my memory barriers, I submit that to a pipeline barrier, record that, and submit it right before I do a command copy buffer to image. I'm using the host stage bit because my previous access was on the host, and then I'm doing transfer stage bit because the thing I'm about to do is a transfer task. You then do the command copy buffer to image, and then on the other end, you're about to, say, read it as a texture, so you do another image barrier saying from transfer write to shader read, and again, you do a layout transfer from transfer dest optimal to shader read, and then another pipeline barrier to finish off that set of transitions. So it's kind of a lot of stuff to think about. Once you've got your head around it, it seems like it's easier. I mean, people seem to have a click moment where they go, I get it now. I would say that if you're trying to get your head around this, don't do it via porting from GL and then figuring it out afterwards. Go and have a look at it first. Because it's intuitive once you understand it, but until you do understand it, it can be a pain in the ass. So there is another way of doing all of this type of stuff. Pipeline barrier operation in particular, they're almost always doable, or usually doable via render passes, at least for drawing operations. We haven't got anything like that for compute at the moment. For drawing operations, you can do this. A render pass, which the ARM guys talked about a minute ago, that's basically a dependency graph for your rendering. You say what is happening between these things, and that's how tiled GPU, for instance, can merge subpasses to go, well, I can just use pixel storage for this. And again, on desktop, even then, it allows you to plan ahead to figure out what kind of transitions you're going to do. One of the nice things is that you don't have to track the layout transitions between subpasses. You just say, this is what I'm using in this subpass. And however the driver has decided to execute the render pass, it will do the layout transition tracking for you for that, because it doesn't have to actually track anything because you've already told it. which is a much cleaner way of doing things and maybe something we should explore in the future. But they can be much more efficient than manual barriers because of that, because again, it's about giving the driver, the implementation, the opportunity to plan ahead, which you don't get when you're recording a command buffer, which you want to do typically very fast. So I'm not going to just go into the whole thing of what a render pass is, but I will talk about subpass dependencies, which are the synchronization mechanism within them. So these basically take similar info to pipeline barriers. They're explicitly between two subpasses within a render pass. They look a bit like, rather than having a set of memory barriers associated with them, you basically get the bits that would be a global memory barrier. So you've got the stage masks from the pipeline barrier, and you've got the access masks from the memory barrier. You also have this dependency flags, which I haven't really talked about yet, but they're particularly relevant with regard to subpass dependencies. These you can set here. There's one flag here, which is dependency by region bit. By setting that, you're saying to the driver, or the implementation, I've only got a one-to-one pixel mapping. So for stuff like the multipass gbuffer stuff, we're only accessing the same pixel location for each subsequent pixel in each subpass. So if you're 1-1, the data you want was written by pixel 1-1 in the previous subpass, you want to set that flag because that's the thing, that one flag is the thing that allows tilers to fuse stuff. Without that flag, no fusing will happen. With that flag, fusing will happen. So please use it. This is sort of one of the particularly bad cases of if you get this wrong, bad performance will ensue. They're a little weirdly flexible. You can also do something called a subpass self-dependency. Subpasses can wait on themselves, which sounds highly unintuitive. This isn't some sort of cyclical nonsense. What this basically says is now you can do a pipeline barrier within a subpass. They have specific rules. In order to preserve the sort of atomicity of a subpass, we say you can only make forward progress. So you can only ever wait on the same or later pipeline stage, at least for the fragment stuff. And for fragment space pipeline stages, you have to set the dependency by region bit. The main time you would use this is if you're doing some sort of order-independent transparency techniques. Rather than using multiple subpasses, it would be generally more efficient to do self-dependencies, because then you can do draw, self-dependency, draw, self-dependency. I'm not going to go into too much detail how you do that, but obviously if anyone's interested, they can talk to me afterwards. The other one is subpass external dependencies, and these are kind of quite a nice, useful one, particularly for presentation, which I'll go into in a second. But the idea here is that you can basically depend on stuff that happened before the render pass started, which basically gives you a way to do a pipeline barrier, but as part of a render pass, at least to a degree. It's very useful for some common dependencies. Present source to color attachment output is very useful and avoids a pipeline barrier. So again, it gives the driver the opportunity to plan ahead. One thing that's not been shown yet, because it's part of a different structure definition, is you also get a layout on the subpass to say which layout it's in. I did mention that a minute ago. And you also, on the render pass, get an initial layout and a final layout, which is, so you have all that information separately to this structure. So you don't have to, as I said, track. You don't have an old and new layout for these things. You just say, this is the layout I want at this point, and it knows that the old layout before that was whatever was the previous subpass that the driver schedules. So it's quite neat from that perspective. So the way to sort of do the other half, whenever you do a subpass dependency like this, you also have the option to do a command wait events within your buffer as well, render pass as well, which will set a bit more stuff going on. Yeah. Right, sorry. So here's a quick-ish, again, sorry, acquire, render, and present example. And this is actually only half of the story, but you'll see in a minute why that is. So typically if you've only got one render pass, or if you've got multiple render passes in your scene, what you want to do is actually put the acquire barrier bit into the render pass. So you set your first subpass dependency, for instance, could be an external dependency. You're waiting on an external subpass, which is stuff for the render pass. You haven't got, you want it before the first subpass that it's used in. It doesn't have to be 0, it just is in this example. And then you don't actually have to wait on anything particularly, because you've got semaphores, which I'll go into in a minute to guarantee that. So you just have to wait on, is this command buffer running? So that's what top of pipe basically means. And then you have to wait on color attachment output, which is the latest possible stage that you can wait on before the image needs to be rendered. Like you could think, oh, maybe it's fragment shader. It's not fragment shader, it's color attachment output bit, which is the latest stage that you will need to actually access that thing, the presentable image. And similarly for the access masks, we've already guaranteed that it's in device memory because of the semaphore. Again, I'll go to that in a second. So I don't have to do any access mask thing here. But I do need to say where it's going. So I'm saying it's going to color attachment write bit. So now I can write safely to the color attachment. And at the other end, you'll need sort of the last subpass it's used in, and then external for the destination, so everything that happens after the render pass. And then you do basically the same thing. The source stage mask, you make the earliest possible stage it can wait on, and the destination stage mask, the latest, because that basically gives you the maximum overlap. So the earliest is, well, we've written it in the color attachment output stage, so that's the stage I'm setting for my source stage. And similar again, we've got the semaphore submit stuff guaranteeing you don't actually need to wait on anything. So you just say, well, fine, end of submission of the command buffer is what I'm waiting. It's going to wait on this. So as long as that command buffer is executed, you know it's safe. Ditto for the access masks. Again, color attachment write as the source, and don't care about the destination because it's going to be guaranteed to be in device memory anyway. Once you've done that, you can then acquire the image, submit, which includes the execution of the render pass, and then present, and that all sort of works, except you also need semaphores. So those three operations, those three operations at the bottom are all kind of sort of queue operations-ish. But one thing they all do is they all take semaphores to synchronize how they are executed between them. So a semaphore is basically used to synchronize queues and other external things that aren't queues, but not the CPU. They're pretty coarse. They're per sort of batch of things you submit. So in a submit info, which is what I've got up there, which is a set of command buffers, you can say all of these wait on these semaphores, and then it'll signal these semaphores. And you can have multiple per submit command, and you can also have multiple per batch as well. There are some implicit memory dependencies here. So I actually kind of wish I had my memory space thing, but I'll just quickly go back to it. I don't know why I haven't included that slide here now. I think about it. Wow, this is slow. Right. Oh my God. Come on. Back. But wow. Okay. It's just there's one missing. It's fine. Okay. So basically, what a semaphore guarantees is that anything that's in here in the pipeline stages, or in here, which is the host transfer, we'll make it there. That's basically what it guarantees. So you don't have to do a manual pipeline barrier. It doesn't guarantee anything else other than that. But it does save you some pipeline barriers. It's basically like an implicit flush and invalidate at the end of whenever you have a semaphore blocking two things. And now I've got to get back to that same slide again, so bear with me. OK, holding it down is much faster. Ah, that was quick. Too quick. Right, so that is all guaranteed for you. So that's when I was saying, you don't have to worry about the source stage and the destination stage. In the previous example, that's because the semaphore has already guaranteed that. It's like the access mask's already taken care of. It includes all of those access masks, basically. And you don't have to care about the stages because you're basically saying, after this thing has been submitted, do this other thing. So like I say, quite coarse-grained. So this is the second half of the acquire, render, present stuff. So we'll start with the acquire. You basically pop a semaphore in there to wait on. So basically that will signal once the presentation engine has actually given you that image back and said, you have ownership now. Because you can basically get the handle back before it's actually ready to render. You then, when you submit your command buffers, you put the acquire semaphore in there so that you know that that command buffer won't do anything, or at least won't do anything that depends on that image until it gets that acquire semaphore. And then at the end, you also want to signal a semaphore, which is saying my graphics work is now done. And then you can submit that to the graphics queue, and lovely, off you go and do the semaphore things. And then finally, you have a present, which is going to put the thing on screen. And you don't want that to fire off until your graphics work is done, executing. So you'll wait on the graphics semaphore and then submit the present. And once everything, then it should just tick over quite nicely. And it will be serialized, the acquire, and then the raster, and then the present, because you want it to be. But everything else should be able to carry on as normal. So the other synchronization primitive that's quite important, well, they're all important, is fences. So these are used to synchronize the queue to the CPU. They are even more coarse-grained. That's one per submit command. As you can see, qsubmit takes one, and then there's a bunch of other stuff for manipulating fences. They have the same implicit memory dependencies as semaphores. But the thing that they mainly include is the idea that you can sort of submit one, and then basically you can poll it on the CPU and go, well, when this is done, I know everything I just submitted, the GPU is not using it anymore. So if you have any resources, or if you want to reuse command buffers, anything you want to reuse, you wait on that one fence, which saves you tracking each resource individually, because if you're doing that, you're doing it wrong, I'm afraid. I'm nearly done. I'm a little over time, sorry. So there's a couple other bits of important synchronization. Queue submission. This is kind of actually the most important of all the things. If you don't submit anything, nothing will happen. This is basically used to push your recorded command buffers to device. It does make guaranteed forward progress, so it's a little wishy-washy what that actually means, but it basically means if you submit something within finite time, the thing will complete as long as there's no blocking synchronization on it. And again, they have an implicit memory dependency. I'm not going to go scrolling all the way back again, but from host memory, anything that you've written that is mapped to device memory will be flushed to host transfer. Oh, sorry, to device. Oh, no, it's actually more than that. It's actually to all the pipeline stages. So anything you've written will go to all the pipeline stages. There's also two others. There's the wait idle commands, which if you use, there are two reasons you would use these. One is for debugging. The other is clean up at the end of day. If you use it for anything else, it's either to work around a driver bug, or again, someone's going to yell at you for doing it wrong. Because it's very, very heavyweight. It's basically like, you know, that situation at the start where I said, don't do this, where CPU and GPU were completely not overlapped. That will happen if you use those. But that is useful for some very small set of circumstances. Oh, I actually had a warning. OK. So last slide, I promise. Programmer guidelines. This one's probably the trickiest bit. Specify exactly the right amount of synchronization. If you do too much, you'll starve your GPU. And if you miss any, things will blow up in your face. Now, I actually should have updated this slide. I say you use validation layers to help. They won't cache everything, improving over time. RenderDoc's actually doing a lot better at this sort of stuff at the moment. So I would strongly advise using RenderDoc to help you with this, because it's got some really nice debugging for this sort of stuff. You do need to pay particular attention to pipeline stages. They are fiddly at first, again, especially if you're coming at an angle from GL, how do I port? But once you've actually got them, there seems to be a click moment for most people. It's like, I get this now. Do think about image layouts. They're a bit tricky, but if you can use them, take advantage of them, you can save some bandwidth. In GL, this would have been handled for you. In Vulkan, it's not. So you may see a performance regression if you're not careful with them. Always prefer render passes. Because of the whole planning ahead thing, they give you a lot of efficiency. And do pay attention to implicit dependencies. There's no point doing a pipeline barrier if you know your semaphore or your submit is taking care of the thing you were trying to do anyway. And finally, and probably the most annoying one, there is going to be different behavior on different implementations. That whole scenario of what might happen if you get it wrong, that will happen sort of consistently on one vendor, but across vendors, it could be anything. It might be no ops for some things. It might be completely required for other things. So you do need to test. But hopefully, validation layers and RenderDoc will get you most of the way there. And that's it. A couple minutes for questions.
There will also be the panel after for more synchronization fun.
Yeah, sorry to monopolise the questions, but so one thing I was interested in is whether we need more than one semaphore in the case where we may have execution which is overlapping. So, for instance, having more than one acquire semaphore, because potentially we could signal it before we wait on it.
Yep, sorry. Sorry, are you specifically talking about acquire? Sorry.
Yes. So let's take for example the acquire semaphore. When you acquire it, you essentially sort of queue up something which says we're going to acquire it. That may happen asynchronously. Do we then need more than one acquire semaphore in the case where we may be then rendering the next frame? Oh,
right, yes. So you'll need one per frame. So as with resources I mentioned before, you should use fences to figure out what your reuse strategy is there.
Because all the samples I've seen have only used one, and that kind of worried me.
That sounds bad. I think it's potentially possible if you use the right strategy, but it's kind of it's better to do the ring buffer.
Because a lot of the samples have to wait for device idle anyway.
Yes,
so
all the way device idle is a plague, and we should purge
not a
it,
good
but
thing.
yeah.
The other question I have is, are there any implicit memory barriers between commands in the same command buffer at all, or do you always have to put a memory barrier in?
There's only a couple of things. I mean, there's some stuff about like a few ordering guarantees being made by the GPU. I wouldn't say anything's at the level of a pipeline barrier. The only things that spring to mind are the rasterization order. That's a thing that's been there since day dot, because that's Painter's algorithm. That's there. And if you do image layout transitions, the order they're submitted in, they will always execute fully in that order, so you'd have to synchronize those explicitly. And pipeline barriers themselves, synchronization things themselves, will always execute at top of pipe, I think. Or at least they, yeah. There's a few bits and bobs, but there's nothing that's, I will automatically do anything for you. It's just things that kind of fall out of how things have to work.
So we should definitely put barriers between compute
if you need
dispatches, for
synchronization,
example.
put synchronization down.
Yeah. Okay, thanks very much.